Okay, so let me start with a review of what we discussed on Tuesday. Let me come back here. So we were talking about the thrust required for an aircraft, and the required thrust for an aircraft depends on speed, and we showed where this dependence comes from. Basically, we just had lift and drag, aerodynamic lift and drag equations, and the drag polar equation that connects the lift force to drag force. So from this equation we obtained this equation for the drag force, and this drag force has dependence on the flight speed, obviously. So the two parts has different dependencies. One part decreases with increasing speed, and the other part increases with increasing speed, and if you add the two you get this curve. Okay, and then so I showed you that the minimum point where the drag force becomes minimum corresponds to the case where the lift to drag ratio is maximum. So which is, I think, reasonable to expect, right? Because lift force is something useful. We want lift force to be as large as possible, and drag force is bad. We don't want any drag force at all. And normally, intuitively, we expect that this ratio must be large. And here on this graph, we see that, in fact, the minimum thrust point corresponds to the case where this ratio is maximum. Okay, so if you can increase this ratio, then you will increase the overall performance of your aircraft. So this is the fundamental aerodynamic parameter in aircraft design. So we aim to make this ratio as large as possible. And then I told you that if you have the drag polar data obtained experimentally, then you can find this ratio graphically by simply drawing a straight line from the origin that is tangent to this curve, and the point where they meet gives you the maximum lift to drag ratio point. And then if you know your drag force, then there are two possibilities for an equilibrium flight, for a steady level flight, and you see these possibilities on this graph here. So you can either be flying at this point of the drag curve or this point of the drag curve, and you can find the intersecting points either graphically. From the graph we can read what the corresponding speed values are, or you can use the equation and find the exact speed values. So from this curve we can already find the maximum speed of an aircraft. So the maximum speed will be achieved when the engines are producing the maximum possible thrust. And for example, if the maximum thrust value is this much, then this is the maximum flight speed of your aircraft, maximum cruising flight. So you should be careful about that. So remember, this curve is for steady level flight only, and the maximum steady level flight speed is then found by using the maximum engine thrust. And if you want to find the numbers using equations, then you go back to the same equation, and for the thrust value you simply put the maximum available thrust value. So let me just quickly pass here. Okay, also on Tuesday I started talking about propulsive characteristics. So propulsion system is the system that produces the thrust force. So this is actually the engine of our aircraft, and there are different types of engines used, but they all work on the same physical principles of the Newton's laws of motion. Okay, so if you look at this diagram here, so what you see here represents the propulsion device. So this could be either a jet engine or it could be a propeller used to create the thrust force. It doesn't matter what that device is. If you look at how it works, a certain amount of air goes into the propulsion device, and the same amount of air leaves the engine. Okay, so there's no air accumulation within the engine. So whatever goes in just goes out. But the difference is the propulsion device or the engine accelerates the air. Okay, so the entering air has a certain speed, and as it leaves the engine, it leaves with an increased speed. So if you call the inlet speed V infinity, the exit speed is Vj, and Vj is always greater than V infinity. So how is that possible? Some force must have been applied on air, right? So for it to accelerate from the second law of motion. And from the third law of motion, the same amount of force should be applied as a reaction on the engine itself. So the force that accelerates air is towards right, and the reaction force that is applied on the engine is towards left, and this force forms the thrust force of the engine. Okay, so this is common for all types of engines used on aircraft. And we call these engines air-breathing engines because they breathe air, and air goes into the engine and it exhales air from the exit. Okay, so I'll be talking more about this engine, but before that, on Tuesday I tried to explain the efficiency of the engines. And to explain aircraft engine efficiency, I gave you some examples because I think these examples make it much easier to understand about the efficiency of an force generating system. Okay, so basically the idea is whenever you spend some energy to get some useful work, you don't always convert all that energy into useful work for your purposes. Sometimes some part of the work is wasted, and it's very easy to see this in these examples. So if we start here, there's a person here, and the person pushes himself against a wall. Okay, so this is a wall, and since wall is stationary, it's fixed, as he pushes himself, he starts moving in the opposite direction, and assuming that there's no friction on the wall, he's just skating on ice. So he will gain some speed, right? So here you can say that all his energy turns into useful kinetic energy for this person. But if you consider this case, whereas instead of a fixed wall, he is pushing another person. Okay, since this what he is pushing against is not constant, as he applies the force towards that thing will start moving as well. Okay, so in this case, he will start moving, but some part of the energy is now transferred to this other object, right? This other person. So if you compare the two, if you assume that he's applying the same amount of force, the acceleration he can get in this case will be greater compared to this case, because this case, some part of his efforts accelerates this other object. Okay, so this is very easy to understand, right? Do you have a question? Okay, so even though he spends the same amount of effort to accelerate himself, he gets a higher acceleration here, whereas his acceleration will be smaller. And the reason is some part of his effort goes into accelerating this object, and this is a waste for the purpose of accelerating this person, right? If the goal is to give this person energy, the energy that goes into the other person is a waste. Again, the same example in the same type of loss viewed in a different example is that this person is climbing a rope, and if the rope is attached to the fixed ceiling, then the ceiling will not be gaining any energy because it's fixed. He's not adding any energy to the ceiling, so all his effort turns into useful energy for himself. Whereas in this case, it's not attached to a fixed object, but it's attached to a free mass through a pulley here. So as he pulls on this rope, well, depending on these masses, he will either be adding all energy to this mass, the mass will be going up, so the energy will be transferred to the mass, or it may be split between the two, right? He may be climbing a little, and then mass will be climbing as well. So the energy will be split between the two. So again, if you compare the two, here the efficiency is 100%. If you ignore the efficiency is lost, or the energy lost in friction or things like that, all his energy becomes useful for him, whereas here the energy that goes into the mass is a loss. Okay? So this is a very important point to understand efficiencies of aircraft engines. Okay, now let me come back to today's topic. Okay, now we come back to the same the diagram as before. So as I said, a certain amount of air goes into the engine, and it exits the engine with an increased speed. And this is necessary for thrust generation, by the way. But if you look at the air exiting, since it has an increased velocity, that means the air exiting the engine has some energy added to it. Okay? And this energy is wasted because you're throwing some accelerated air into the atmosphere. And that's not your purpose. Your purpose is to get thrust force on your engine. But while doing that, you eject some high energy air into the atmosphere. And that's the loss. So let's take a look at some equations and see how much of energy is really being lost. So from here we can see that we are losing some energy. And again, let's try to see, quantify that, how much of that energy is lost, and if there's anything we can do about that. Okay, so before this, let's try to find an expression for the thrust of the engine. So let me start by writing the Newton's second law of motion, which is F is equal to ma, right? So this is the Newton's second law of motion as we used before, which is mass times dV by dt, right? But this is actually not the most general form. This is a special case of this equation where mass is constant. Okay? So in the actual form of this equation is as follows. It is the time rate of change of momentum of your object. Okay, so this m times v is the momentum, right? You know this from your physics course. So normally this equation is in this form, but for mechanical objects we say that mass is constant, so we take this outside the equation, and then that becomes m times a. But in this case, let's go back to the original form of the equation, and so we can actually write it as limit as delta t goes to 0 of delta momentum divided by delta t. Okay? Okay, so let me write some explanation here. Let's assume that within time delta t, the amount of air that goes into the engine is delta m. Delta m, okay, so let me write it. In this case, the momentum of the air going in is equal to so let me call it m in. Delta m times the speed, and speed is v infinity. And the momentum of the air exiting the engine is, let me call that m out, and this is going to be delta m times vj, right? Because the output speed is vj, and the same amount of air goes out since no mass is lost in the engine. Obviously, what goes in should go out. Okay, so okay, then we can write delta momentum over delta t as so this is the exit momentum minus the inlet momentum v infinity divided by dt, and you can write it further as delta m parentheses vj minus v infinity divided by delta t. And if you take the limit, you can write this as m dot times vj minus v infinity. Okay? And this is actually the thrust force. Okay, so it's just the application of Newton's second law of motion. So if you just look at the momentum of the air entering the engine and leaving the engine, you can conclude that this much force must have been applied on the air to increase its momentum. Okay? And the same amount of force must be applied by the air on the engine, and that force is what we call the thrust force. Okay? So let me now add a note here that so the thrust of an air breathing engine depends on mass flow rate and the speed increase of the air. Okay. Now let's take a look at the energy increase in the flow as air accelerates. Its kinetic energy increases, and this is actually lost energy for our purpose, since our purpose is to generate thrust force and not to accelerate air. So this is a good note, so let me actually add that there. So there are two things that determine the amount of thrust produced by an engine. These are mass flow rate, mdot, and speed difference. To get large thrust, you need to make both of these large. Okay, so if you want to have a very large thrust force, then that means you have to pass a large amount of air through the engine, and also you need to give this air a high acceleration, right? You need to accelerate that air as much as possible. Now let's take a look at the kinetic energy. Now let's take a look at how much energy we actually lose into the atmosphere. So within time delta t, delta m amount of air flows through the engine, and the kinetic energy increase for this air is given by so this is kinetic energy added to air is 1/2 times delta m times Vj minus V infinity square. Okay, so this is the kinetic energy of the air exiting the engine. Okay, now so let's go to power. So let's again, you know this from your physics courses. Power is defined as energy per unit time, mechanical power. So if you have force, then the energy due to that force is force times distance, and if you consider the per unit time for this energy, you can write power as force times velocity, and power wasted into atmosphere with exiting air is energy per unit time, right? And this is energy. So per unit time you make delta m divided by delta t. From there you get an m dot term. So the power you waste into atmosphere becomes 1/2 times m dot times Vj minus V infinity square. Okay, now let me just summarize what we have found so far. So for thrust, we require m dot. Okay, so this is what we need. We also need speed difference, Vj minus V infinity. Then thrust is the multiplication of the two, and that times Vj times V infinity, and lost power is, let me say, wasted power. It's 1/2 times, and that times Vj minus V infinity squared. Okay? Okay, so if you see a conflict here, right? So if you want more thrust force, you want more airflow. But if you look at how much power you waste, if as you increase airflow, you increase the amount of power you waste as well. Similarly, if you want more thrust force, you can increase the exit speed of the air. But if you do that, you increase the amount of power you waste as well, right? And there's nothing you can do about that. If you say, I don't want to waste any power at all, then you should either set m dot to 0 or the speed increase to 0. But if you do any of that, then your thrust force will become 0 as well. So this just comes from the nature of the problem, that if you want to create thrust force, you need to waste some of it. And you can't really do it any other way. So you cannot, at least using an air-breathing engine like that, you cannot create thrust force with 100% efficiency. Okay? Evet. So that's a good question. That's because okay, so I was talking about this picture here, right? And here I said that the air entering the engine has speed V infinity, and the air leaving the engine has speed Vj. But that's not really the situation in reality. In reality, the atmosphere is still, right? The air has actually no energy to begin with. It's just that the engine flies into air with speed V infinity. So in reality, the air, before it goes into engine, has no speed, unless there are winds in the atmosphere. So our assumption is that there are no winds, so atmosphere is stationary. In that case, before it goes into engine, the air has no energy because its speed is 0. İşte onu diyorum, ilk başta kinetik enerji yok. Çünkü ilk başta akış yok. Yani ondan diğerini çıkarttığınızda neden farklı interesi oluyor da İşte onu açıklamaya çalışıyorum yani bu biraz kafa karıştırıyor bu noktada. Şimdi ben diyorum ki giriş hızı V sonsuz, çıkış hızı Vj diyorum ya. Bu V sonsuz uçağın hızından kaynaklanan giriş hızı. Yani aslında hava duruyor, uçak havaya doğru V sonsuz hızıyla ilerliyor ya. Şimdi o şekilde düşünürsen, dünyaya göre baktığın zaman havanın motora girmeden önce bir hızı yok. Değil mi? Havanın hızı 0. Dolayısıyla inlet enerjisi 0. Çünkü hızı 0. Çıkışa baktığın zaman da atmosfer, dünyaya göre baktığın zaman çıkan şeyin hızı, havanın hızı Vj eksi V sonsuz. Çünkü o kadarlık bir ivmelenme, hız artışı oluyor. So the inlet kinetic energy of the air is 0, and the exit speed is Vj minus V infinity, because that's the amount of speed added to the flow. Okay, so this is really important. Let me just finish with that. Okay, so suppose that I want a certain amount of thrust, right? I'm designing an aircraft engine, and let's say the m dot is A units, whatever that A is, and the speed increase is B units, okay? And in this case, the thrust force will be A times P, right? Because it's just multiplication of the two. And the waste power is 1 over 2 times A times B squared, right? Okay, so what if I change these quantities? Okay, so I still want the same amount of thrust force. I don't want the thrust force to change because I need certain amount for the performance of my aircraft. So what if I increase the airflow? So let me make m dot 2 times A, and let me make the speed increase 1 over 2 times B. Okay, so I did two things. So I'm increasing one of them and decreasing the other, such that the multiplication really gives me AB, right? As I multiply these two, I get AB, the same thrust force as before. But if you look at the waste power will be 1 over 2 times 2A times B squared, which is 1 over 2 B squared. And this is equal to 1 over 4 times AB squared, right? So that means I'm generating the same thrust power as before, but I'm wasting half the power I wasted previously. Okay, so this is because you have the speed difference here, but you have the square of the speed difference in this equation. So this is a good thing, right? Apparently I can generate, if I adjust the mass flow rate and speed increase in such a way that I change them as you see here, in this case I get the same thrust force with less wasted power. Okay, so based on this, then I can do this as well. Instead of increasing this by a factor of 2, I can increase that by a factor of n, and I can reduce the speed increase by the same ratio, 1 over n times b. Then the thrust will be the same, but the wasted power will be 1 over n times 1 over 2 ab squared. Right? So that means if I can make n a very large number, by keeping the thrust output the same, I can reduce the wasted power. Right? If you make n, for example, 100, then the wasted power will be just 1% of the initial wasted power here. Okay? Does this make sense? So this is a very fundamental information. It just comes from the very basic physics laws, right? Very basic laws of physics. And there's really no doubt about these equations. And it's a very known fact that if you want to increase the efficiency of your engine, which means if you want to reduce the amount of power you waste in the atmosphere, this is in fact what you need to do. You need to increase the air intake as much as you can, and you need to reduce the speed difference. So ideally you want to take a very large amount of air, and you need to give it a very little acceleration. And if you can do that, that means you waste very little power in the atmosphere, and most of the power you spend by burning fuel goes into useful thrust force. Okay? I'm going to show you some examples from real aircraft. So actually there are two examples of this. So maybe I can... I'm going to show you two extreme examples of this. The first one is the helicopter. So this is the helicopter rotor, helicopters have really large rotors to create the force to carry the weight of the helicopter, and the amount of air that flows through that very large rotor is really high. So the two extreme examples to our discussion before is helicopter and a jet engine. So in the case of a helicopter, you have a very large disk area, and that allows a lot of air to flow through that propeller or helicopter rotor in this case. But the speed increase is really low. So in the case of a helicopter, the speed increases on the order of 10 meters per second. Okay, so if the helicopter is in hover position, and if you measure the air, the speed of the air that goes down the helicopter rotor, it's on the order of 10 meters per second. And a lot of the MDOT is really large because there's a huge area that air can flow through. If you compare this to a jet aircraft that with hovering capability like the Harrier, in that case the situation is the opposite. So the Harrier uses jet flow, right? That means the air flows through a much smaller area. So the MDOT in this case is very, very small compared to the MDOT of the helicopter. You can still get very large thrust force, and the way to do that is you need to give the air a very large acceleration. Okay. So in the case of helicopter, the speed increase is only 10 meters per second, but in the case of Harrier, well, I don't really have an exact number, but I can say that it's on the order of 100 meters per second or even more. Okay, so with a Harrier, you can create a vertical force equal to the weight of the aircraft, but if you look at how efficient that engine is, it's very, very low compared to a helicopter, and that's because you have very little mass flow and a very large acceleration. Okay, so because of that, helicopters are ideal for hovering. So a helicopter can hover for more than an hour with a certain amount of fuel. But if with the same amount of fuel, a Harrier, for example, can hover only for just a couple of minutes. In fact, this vertical takeoff and landing with a jet aircraft like this and this includes F-35 as well, the newest F-35, it has a vertical takeoff landing version. It uses the same jet flow, and the process is so inefficient that a Harrier consumes a third of its entire fuel just for takeoff and landing. So just for takeoff and then landing, it uses 1/3 of its fuel. Because the process is has very poor efficiency. Okay. Do you have any questions? I'm going to show you a very good example showing the application of this principle. I was looking at these pictures. So this is the Boeing 737 aircraft. So this is one of the very common airplanes flying today. So let's take a look at its development. So this is the first version of 737. This is 737-100. Okay, this one, 737-100. And look at its engines. So this is the engine inlet area, right? This circle here. So it was using a turbofan engine with a certain amount of inlet area. Then in the newer generations, to increase the efficiency of the airplane, they replaced the engines with more efficient engines. And more efficient means what I just said. More efficient means can take more air in and give it a smaller acceleration. So if you look at the current version, this is this for example. So the area here is larger, and if you look at that, it's not perfectly circular, right? So has this elliptical shape. And I was always curious about this. I was saying, why these engines are not circular? Because all the other engines have circular inlets, whereas this one doesn't. The reason for that is, while improving the design, they didn't want to change the landing gear system. Okay, and it has a certain ground clearance, right? So the distance between the wing and the ground is so much. So to leave sufficient clearance here, they had to use this as such a weird shape. So they wanted to make the inlet very large, but the ground clearance didn't allow enough room, and they didn't want to change the landing gear setup either, because once they change the landing gear setup, they have to repeat all the tests related to the landing gears. So it will be a lot of additional cost. So to be able to fit larger inlet area, they use this setup. Okay, so they increase the area towards sides. So this is more efficient. And now they're working on the newest version of the same aircraft. So this is not flying yet, 737-900. And if you look at here, now they finally changed landing gear design. And it says here, new extended main landing gears. They increase the height of the aircraft from ground, and the only purpose for doing that is they want to be able to fit in engines with a larger diameter. Okay, and if you look at the diameter here of the future generation, if you compare it with the first generation, there's a tremendous difference between the engine inlet area. That means the newest version will be much more efficient. Okay? Do you have any questions? Well, if you just look at the area here, I would say it's about at least 3 or 4 times larger, right? The newest one, this one. So this is almost comparable to the fuselage diameter. Still smaller than that, but it's almost comparable. Whereas if you look at this one, this is much smaller compared to the fuselage. So I don't know why they used such an engine in the first version. Obviously they knew that the efficiency is related to how much air you can take in, but probably at the time the engine technology was not allowing for such a large diameter engines. But now today they can do that, and they're doing it to increase the efficiency. No, I don't remember that. Well, the engine, it needs to be circular because it's rotating, right? I will be explaining that as well, but I will do that next week. So if you look at inside of a jet engine, you have circulating parts, you have rotating parts, and for good balance, it needs to be a circle, because if you want to rotate any other shape, a non-circular shape, you will have a lot of vibrations. So to prevent that, it needs to be perfectly circular, whatever rotates. So even in this case, you have a circular engine here, but they increase the inlet area to let more air in. But what's rotating inside is again a circle. Mm-hmm. Voila. Mm-hmm. Arkada olmasının avantajları var. Bir kere yani önü temiz oluyor, arkada kalıyor mesela önde olduğu zaman pervane, kanadın üzerinden ya da diğer konta üzerinden akan hava pervaneden çıkan hava olduğu için o çok düzgün bir hava değil tabii. Yani oradan geçen hava o pervanenin dönme etkisiyle o dönerek bir hava çıkıyor neticede. O yüzden arkada olması avantaj. Arkada olduğu zaman daha temiz bir hava görüyor kanat ve diğer şeyler. Önde olmanın avantajını çok bilmiyorum işin aslı. Yani niye hep önüne koyarlar? Yani insan uçak da var pervanesi arkada olan. Ama çoğunluk tabii önde. Bilmiyorum açıkçası niye önde yapıyorlar. Çünkü arkada olması bari daha avantajlı. Hı hı. Çekiyor. Yo, yine bir thrust force'u. Önde olduğu zaman da pervane üzerinde bir thrust kuvveti oluşuyor. O thrust kuvveti ileri doğru götürüyor. Hı hı. Niye arkada iki tane olması gereksin ki? Arkada da bir tane büyük olabilir. Ha. Evet. Ya açıkçası niye önde tercih ediliyor onun çok şeylerini bilmiyorum. Mutlaka ki vardır sebepleri de. Ama arkadaşın haklı yani. Genelde insan araçlarda çoğunlukla arkada tercih ediliyor. Arkada olan örnek bayağı fazla. İnsanlarda da var ama tek tük. Genelde çoğunluk öndeki pervane kullanıyor. Okay, so our time is up. Let me stop here. And next week I will continue with the types of engines, jet engines and propeller engines.